Howdy y'all, and welcome back to our course, Databases Demystified, sponsored by Fivetran. I'm your host, Michael Kaminsky. Today we're going to be talking about query planning and optimization, which is a critically important topic for anyone who spends a lot of time working with databases. So what is query planning? A query, normally written in SQL, is how we tell the database what it is that we want. But then the database itself is in charge of figuring out how to go and get the data out of whatever format it's stored in on disk. Sometimes that might involve lots of intermediate computations, in addition to just finding the right data. The query plan is what the database uses to actually go and execute the query that we submitted. It turns out that we can actually review this plan that the query planner generated in order to see what the database is doing under the hood. So a quick review. SQL, SQL, stands for Structured Query Language, and there are two really key things to know about it as a programming language. One, SQL is not a language, but it's actually a standard that is implemented differently by different databases. So the SQL that you use in your PostgreSQL database probably won't work in your BigQuery database. The SQL syntax is generally pretty similar across these databases, but it's important to know that you can't just easily migrate your SQL from one database to another and expect it to work perfectly. Two, SQL is a declarative language, which means that you describe the output that you want to see rather than giving the computer direct instructions for how to generate that output. We'll talk about this in more detail in a second. As a reminder, here's what SQL looks like. If you spent any time at all working with databases, this should look pretty familiar. Here we've got a traditional query that starts with a select, along with a where clause for filtering, and a create table command from the DDL. In a declarative programming language like SQL, what we're doing is describing the data that we want back, and the database itself will figure out how to execute on that request computationally. That is, we don't concern ourselves with the how, just with the what. This can be confusing for software engineers who are coming to SQL from an imperative programming paradigm like Python or Java or C or a lot of others, but it doesn't make SQL any less valid as a programming language itself. Well, this makes working with SQL very convenient since we only have to think about the what, not the how. It can also make working with SQL feel very opaque. If a query is taking a really long time to complete, it can be difficult to reason about what might be going wrong since the code itself doesn't give many hints. So let's take a look at what happens when you are querying a database. The first thing you do after writing the query and hitting send so that it goes to the database is that the database is going to examine the query and parse it, and then use what it knows about the database to generate a query plan. The query plan is the series of steps the database is going to follow in order to be able to return your results to you. The database will generate a plan for all of the steps in the query before it starts to execute on any of them. Once the database has that plan generated, it will start executing by following all of the steps in the plan. Once all of the steps are completed, the results are finally returned to the user. The part of the database that creates the plan is called the query planner. Query planners in modern databases are very complex and very sophisticated. Fortunately, you don't need to understand how query planners are programmed in order to understand what it is that they're doing and how to interpret the plans that they generate. Unfortunately, query planners are not always optimal. Sometimes we can help out the query planner by using our knowledge of the query or of the underlying data, or by actually making changes to the database so that the query planner can plan more effectively. So let's take a look at an actual query plan. This is a query plan generated in a PostgreSQL database, but most databases allow you to review a query plan and they'll all look generally somewhat similar. Here we've got a pretty straightforward query, a select and some joins. And what the query plan is showing us is that the steps the database is going to take in order to execute the query. There's a couple of things that we can immediately see from reviewing the plan, and that's these different parts of the query are going to map on to different parts of the plan. We see a couple of things called hash joins, which tells us the way that the database is going to perform the join we've requested. And in particular, we can see that the top hash join maps to the join between the film actor table and the actor table in the query. And of course, we see another hash join for the other join in our query, between the film and the film actor table. The plan is definitely a little bit difficult to read. But by comparing the query with the plan, we can usually identify which parts of the plan are linked to which parts of the query. It's also important to know that the query plan has a tree structure, so the steps are processed in inside-out order. So in this plan, the first step that will be executed is the sequential scan on films, since that's the innermost step in the plan. So if you're looking at query plans being generated by a database, in general, the reason you're doing it is because you've got a query that's very slow and you're trying to figure out how to make it faster. There are lots of different ways to optimize different queries, or even the underlying data, but I want to talk about a few of the ones that I've used most commonly in my work. One really common way of improving the speed of a query, predicate pushdown, basically just means that we want to filter as much data as possible as early as possible. Here's a query with a pattern that's pretty common. We have a big, complicated query with lots of complicated steps in it. Then at the very end, we're filtering down to look at the results for just one user. Depending on the nature of the intermediate queries and how well the query planner is able to parse the query, you could end up processing a whole lot of data that you don't need, since we really are only interested in the results for user number 4. So what we want to do is move this filter up higher into the query, so the database knows it can filter the data first and then perform all of the computations that are required. Very frequently, by moving the filter up in the query, we can dramatically shorten the query time by helping the query planner see that it doesn't actually have to process all of the data for all of the users. Another great example is that we might examine a query plan and see that our query could benefit from indexes. What we see in this plan is that our database is going to do a sequential scan on all of the tables involved in this query. This means the database is going to read the data from disk, row by row, for every row in each of these tables. For big tables, this can be very inefficient. When we see something like this, it often means that we can speed up the relevant query by adding indexes to our database, so the query planner can use a more efficient process for performing the join. If you don't know much about indexes, you should go check out our other episode on indexes and learn all about them. The last important thing to know about optimization is data distribution. In distributed databases, the way the data are distributed across the different nodes can have a big impact on how much data the database needs to process in order to execute a query. In this example, if the data are distributed haphazardly across different nodes, then a join between two tables can end up being very inefficient because the database has to move a lot of data between the different nodes in order to complete the join. Anytime we're moving data between nodes, the query is going to be slow. So what we want to do in this situation is either change how the data are distributed so that the database doesn't have to do this data shuffling, or add another join condition so that the query planner knows that it doesn't have to shuffle all of the data in order to complete the query. A good example of this might be if your data are distributed by user across different nodes, but you're joining on order ID. Then you can speed up the query by adding a join condition on user ID so that you are joining on both order ID and user ID. This is of course assuming that orders belong to users, and so if your data are distributed by user ID, then all of the orders for a user are going to be on the same node. This doesn't change the logic of the query at all, but it does provide extra information to the query planner so that it can perform the join more efficiently. And that's all that we have for today. The important thing to take away from this lesson is that the query planner takes a declarative input, the query, and uses that to create an imperative plan for returning results to the user. And that by inspecting the query plan, we can come up with ideas for how to make our queries faster by either changing the underlying structure of our data or rewriting our queries to give the query planner more information about how a query could be optimized. Thanks for tuning in. Hopefully you learned something today. Don't forget to like our video and subscribe to the channel. We've got lots more great lessons coming up, so stay safe and we'll see you in the next one.